Hey everybody, we are at the last week of content, last week of classes, yay! So, good news is we're not really introducing anything new this week. We're going to still be working with hypothesis testing, but now we're going to use the t-test statistic, which has already also been introduced. We talked about the t-test or t-tables, the t-distribution, when we worked with confidence intervals. And it's going to be the same idea here. So we generally use the z distribution or the z test statistic when we know the population standard deviation and we have a sample size that's bigger than 30. And also the data had to be quantitative and it had to be obtained via a random sample. Those last two I just stated also applies to the t-test. You can see that under assumptions, numbers 1 and 2, data is quantitative, obtained blah 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 words, and obtained via a random sample of size n. The difference is right here. We're going to use the t-test statistic when we have a sample size bigger than 30, so n is larger than 30, and we don't know the standard deviation, the population standard deviation. So to calculate this test statistic, and let me zoom in here actually. It's very similar to the formula we used to calculate the z-test statistic. It's just pretty much one major change right here is instead of using the population standard deviation, which is sigma, we're going to have to use the sample standard deviation because, once again, there could be cases where we don't know the population standard deviation. That's when we bring in the t. So x bar is the sample mean minus mu naught or mu sub 0. This refers to the population mean that is given in the null hypothesis. And then we divide that by the sample standard deviation divided by the square root of the sample size. Otherwise, the steps to do hypothesis testing are exactly the same. We're going to follow the same process and we're going to work through 3 problems together. Okay, first example. Using traditional methods, it takes 11.2 hours to receive a basic driving license. You know what? I'm going to start highlighting some of these numbers. It takes 11.2 hours to receive a basic driving license. A new license training method using computer-aided instruction has been proposed. A researcher used a technique with 25 students and observed that they had a mean of 11.3 hours with a variance of 4.00. A level of significance of 0.05 will be used to determine if the technique performs differently than the traditional method. Assume the distribution is approximately normal. We're going to make the decision to reject or fail to reject the null hypothesis. Okay, so once again, let me zoom out just a little bit actually. We're going to use the same steps, same order of steps to do this hypothesis test. All that changes is the test statistic. We're going to be using the t-test statistic because, once again, look at this sample size, 25 students. That's smaller than 30. And they also give us the variance of the sample, which from the variance we can determine the standard deviation. So they're not giving us population standard deviation or population variance, they're giving us the sample variance. So this is definitely going to be a t-test statistic. So step 1. The null hypothesis. So remember, the null hypothesis is what we assume to be true. So generally, it's if, a product is designed to perform in a certain way, or if you read the very first sentence of this problem, they say using traditional methods, it takes 11.2 hours to receive a basic driving license. That is our null hypothesis. Now be very careful here. You need to use the proper notation. So the null hypothesis is mu equals, and then we pop in that mean, population mean, 11.2. So I've gotten a few emails about this. When you guys are typing this stuff into Hawks, you have to use proper notation. So Hawks might have the H naught or H sub 0 written out, but then you have to type in this entire piece, mu equals 11.2. And if you don't do that, Hawks is going to mark it wrong because, you need every single piece of this expression here to have a proper null hypothesis. And same for the alternative. If you leave off the mu, it's not a null hypothesis anymore. You need every single piece. So when you're doing your homework, make sure you type it all out. And there's buttons there available for you to do that. All right, alternative. So this is what we're trying to prove. And so if we read the sentence, nothing's going to come from the sample data. The sample data is what we use to calculate the test statistic. I shouldn't say nothing comes from it. We're not going to use the sample data in the creation of our hypotheses. We use the sample data for the test statistic. But they want to figure out if this technique performs differently than the traditional method. They're not saying better than, they're not saying worse than, they're just saying differently. So that tells us they just want to know if mu is not equal to 11.2. So this is going to be a two-tailed test. Anytime we have that not equals to in the alternative hypothesis, it's going to be a two-tailed test. All right, step 2, specify the significance level, which, for us, that's always going to be given. In the real world, if you become a statistician, you will identify the significance level because it's not always going to be given to you, right? Step 3, select the appropriate test statistic and compute. So, when you guys get to the final exam, we're going to be giving you both hypothesis testing problems where we have the Z and the T, and you have to be able to figure out whether to use the Z or the T, right? And again, that all comes down to, do we know the population standard deviation or the sample standard deviation, and look at the sample size. If the sample is bigger than 30, we use Z. If the sample is smaller than 30 or equal to, we're going to use the T. And so, yeah, this is definitely going to be the T test. And let's calculate our statistic. So it's the sample mean. Our sample mean, I have all the sample data highlighted here in pink. 11.3 hours minus our population mean, which comes from the null hypothesis, which is 11.2. Divide that by the sample standard deviation. Now they give us the variance. So I'm going to write it over here. So variance we represent with an S squared, right? So to go from variance to the sample standard deviation, we are going to square root both sides. Square root of 4 is 2. So our sample standard deviation is going to be 2. And then we divide all of this by the square root of the sample size, which is 25. So today I'm not going to be popping over to Desmos. I updated my operating system, and my OneNote always wants to continually sync, which was causing delays from like me writing on my tablet to it showing up on my screen, and it was getting really annoying. So I have to turn off my Wi-Fi now to actually be able to record these videos without a delay. So I did double check all my answers in Desmos. So hopefully I have made no errors, but if you do discover anything, please let me know, and by all means verify everything that I'm doing. But if you pop this into Desmos, you should get 0.25. All right, step 4. Determine the critical values and set up the decision rule. So when we worked with the z-test statistic, you'll be given a table of the critical values. Depending, you have to look up the area and the tail regions, and then you can figure out your critical values from that table that we give you. For the t-test statistic, you're going to have to actually look up the critical values in the t-table. So we're going to do that right now. First, you need 2 pieces of information. So one thing we definitely need is the degrees of freedom. I'm going to label it DF. The degrees of freedom is found by taking the sample size, 25, and subtracting 1. So our degrees of freedom is 24. So we're going to need this piece of information. And we also need to know the area and the tails. Now, if you recall, the t-table, I'll just pop over so I can show you. And I know it looks a little bit different in Hawks. I think they split it up to you click on the t-table for a one-tailed area, or you can click on the t-table for the two-tailed area. The table I have here combines it all into one. But as you can see up here, there's a one-tailed areas, and then there's two-tailed areas, okay? And that all depends on the test that we're doing. Now, if you remember, up here, I already mentioned this is a two-tailed test because we're using the not equals to. So we have a two-tailed area. And the area we are going to look at is our significance level, 0.05. And again, this is in two tails. So on Hawks, you would click on the two-tail t-table. For our purposes, when I look for the area, I'm going to look in this two-tail row for 0.05, which is right here. And then my degrees of freedom is what we look up in this very first column. And the degrees of freedom, I believe, was 24. So we're going to go down until we find the intersection. Let me highlight. 24 and 0.05, we should land at 2.064.